programming this semester. That's how bad it is.
It's all in Java, of course.
Oops. One sec.
7 o'clock. Where is it 7 o'clock from now?
Sammy, are you having a mental breakdown?
Oh,
Oh, no.
wait. Okay.
No, I see what you. No, you're right.
What?
You're right. No, I didn't.
Was there a recording or something like that?
No,
Like,
this is
tomorrow
the.
at time
You're
of
right.
7
You're
o'clock.
right. You're right.
Okay.
Here, it's the local computer that 7 o'clock. My computer is correct.
I see.
Okay. Also, you're having a mental breakdown.
No, I'm also having a mental
Yeah.
breakdown, but I knew that time definitely not them.
Yes. So let's see where we were before Passover. So I'll open up the wiki again to go over the different theorems, also as a recap, also to remind myself where we are. So boundaries, okay. We started studying about sequences and the limits of sequences. We defined what is the limit of a function. We defined what is the limit of a function, whether it's a finite limit or an infinite limit. The first theorem we proved is that if an goes to infinity, then 1 over an goes to 0, and if an goes to 0 and does not equal 0, then 1 over the absolute value of an goes to infinity. And then there are many theorems that help us work with limits. Some of them I proved, some of them I just state. I think this one was the one I stated, that if L1 is a limit of an and L2 is the limit of an, then L1 must equal AT. It couldn't possibly be that the definition of a limit will hold for a certain sequence with two different limits. Quickly, the reason is if L1 is different than L2, take a small enough area, it couldn't possibly include L1 and L2, but it's supposed to include most of the sequence. That's the idea. A sequence with a finite limit is bounded. A sequence tends to L, even if you remove the first element or any finite number of elements that they don't, any change of a finite number of elements does not affect the limit. If all of the sequence is larger than A, the limit is larger or equal to A. I think this one we've proven. An tends to L if and only if the distance between An and L tends to 0. A sequence that tends to 0 times a bounded sequence is important that the second sequence is bounded, because if you take a sequence that tends to 0 and multiply it by a sequence that tends to infinity, the multiplication could be anything you like. But if you take a sequence that goes to 0 and multiply it by a bounded sequence, then the limit is 0. The summation of two sequences that tends to 0 also tends to 0. I think this is where we stop, but let's make sure. Yeah, wow, really. So I did remember. Right? It's an plus bn or the an plus bn, which are smaller than epsilon. Ah, no. We did continue more than that. But we skipped the sandwich one. I don't remember if I told you the theorem. I'll tell you now. Okay. So, the sandwich theorem, if an is smaller than bn, which is smaller than cn, and both of the sequences at the edges tends to L, then the sequence in the middle tends to L as well. And I will write it in the notes in a second. The proof, I just want to say it in general, not give you the full proof. If you take any area of L, after a while, AN will be there. After another while, CN will be there. But because BN is between the two, she must be in the area as well. That's the essence of the proof. You have a question?
When you say it's bigger than or equal to, sorry, it's smaller than or equal to,
Yes.
does that mean that for any n,
Generally, yes.
like, so
It says
A1
so in
will be
Hebrew,
equal
like call n, but if remember always that a finite amount of elements does not affect the limit. So if it, even if it doesn't happen at the start, if from some point on it's true, then it's enough.
No, I'm just trying to figure out exactly what that means. Like AN means
And it's
like
sequence.
that statement. The first statement means that the first element.
Let me
of
try to
AN
answer
will be
it,
smaller than the
and
first
if I'm wrong, then tell me. It doesn't mean that every element of this sequence is smaller than
Right.
every element.
Okay.
But for each index, the element like A10, the 10th element of sorry, the 10th element of A is smaller than the 10th element of B, which is smaller than the 10th element of C. That's what it says. Okay. So I'll write this theorem, and then just before it, we did do this theorem. I think I wrote it completely and proved some of it. Let me make sure. Oh no, I wrote it for multiplication. I wrote it addition, multiplication. Oh, and this I left as an exercise. Okay. And I wrote this. Okay, so I skipped the sandwich one. I will write it now, but I won't prove it. And then I continue to, so just to make sure before I continue, induction. Did everyone here learn induction, mathematical induction? Yes, okay.
We learn it. I don't know if we're good at it, but
Yeah,
it wasn't.
I didn't ask that.
It wasn't discrete.
Yeah, did someone try to teach you? That was my
There wasn't attempt.
question. Yeah, there wasn't. I didn't even ask if you attempted to understand. Okay, no, it's okay because while I will use induction, I will remind you of the idea, but just whether I need to give you a whole introduction or not. And because also induction is not the main subject, it's just a tool, but it is a useful tool that we use every now and again in calculus, but it's usually not as horrible as it is in discrete mathematics. Okay, so the sandwich theorem, the sandwich theorem. I'm not sure if it's called that in English. I think it does. It doesn't matter. One, given three sequences AN, BN, CN, such that for all N, it is true that AN is smaller or equal to BN, which is smaller or equal to CN. Then if AN and BN both tend to the same,
You said CN?
thank you, and CN, both tend to the same limit, L, same limit, because if AN tends to 1 and CN tends to 5, then BN could rock back and forth between the two. Then BN also tends to L. 2. Given two sequences, AN, BN, such that AN for all n, it is true that AN is smaller or equal to BN. That's half a sandwich. And I'll write it in the same articulation. Then if AN tends to infinity, then BN also must tend to infinity. Here you don't need two pieces of the bread, it's just enough to have the one because it goes to infinity. And lastly, I call it sandwich on the floor. Given AN and BN such that for all n, it is true that AN in the absolute value of AN is smaller than BN, then if BN tends to 0, then AN tends to 0. And 3 is easy thanks to 1, because you can say that AN is between minus BN and BN, but I state it because it's super useful. And 1 and 2 are quite easy to prove. I leave it for you as an exercise.
Must be a chair or something.
Oh, yeah, I think it's not full like I am. Okay.
Yeah, one to ring.
Or yeah. Okay. So I wonder if to give you a short history lesson. Yes? Yeah, okay, I like it. Yes. Go, Sammy. Okay. So the question is a question. First of all, intro. Where would you guess that 2 to the power of n tends to? Infinity. That's true. What about 1/2? Let's take 2/3 to the power of n. Zeros. What about 1.0001 to the power of n? Okay, you're right. It didn't point up. It's true, it's infinity. Any number larger than 1, as long as it's fixed, in the power of n tends to infinity. Okay. The question is why? How can one prove that 2 to the n tends to infinity? So I always teach, and I will do as well, using the following modern way, using Bernoulli inequation. I will write it later. But not so long ago, I found out that Euclid had a proof, and Euclid proved that 1/2 to the power of n tends to 0 in a rather geometric way, because that's the way he did everything, right?
Is it with the length of sticks? Didn't you tell us about it? Like you have strips and then you have a smaller strip. And then you take from the bigger strip, the smaller
Yeah,
strips.
did I told you about it?
I think once.
Wow, oh, so I ruined it, so I already give you that,
I mean, maybe people don't remember. Do you know what I'm talking about?
I remember the pictures, I think.
yeah. So I'll draw it up quickly, since I already shown you this. Say you have a bigger, say you have some piece and some value of a segment, the length of a segment, and some smaller lengths of a segment. The claim is if you take half of the bigger segment over and over again, eventually it becomes smaller than the small one. Yeah, I forgot it. Okay, so I'll do it again quickly. Need to change colors. But the idea is that if you multiply the smaller segment enough times, eventually it will pass the big one. That's just division. To divide how many times the small one enters into the big one. And then at each step, you cross out one section of this one and half of the big one, right? And at each time, I always get confused in that. Let me think about it for a second. It always seemed clear to me, and then when I try to explain it, I get confused. And when I take half, so I took half of the, okay. So after I multiplied the short segment, this whole thing is longer than this whole thing. Do you agree? Each time when I take half of that and one piece of that, I definitely make this smaller than this. Why? Because this contains many multiplication of that small piece. So this is less than half of the big one, and this is more than half of the smaller one. So it always stays the case. That's, by the way, to be formal, it also needs induction, but I will skip it. So it's always the case that this piece, the remaining piece, is smaller than that. And you do it over and over again. So we crossed out these two, and then you take half of that, you cross out the half, and you cross out this, and you always take more than half than the small one, and less than half than the big one. So it's always that the small one remains smaller, and eventually after you do it enough times, you actually know the numbers. It's the times that the small piece is contained in the big piece. After you divide by 2 this number of times, you will definitely be left with a smaller piece here than you have here. Okay, so that's Euclid, and not very important, but it's nice, and apparently already told you about it.
How does that show that it tends to 0?
Okay, that's a good argument, and it's a good question. Euclid actually did not define the limit of a sequence, but why does it prove that? Because no matter how small the piece, it's always be smaller, right? So how would you call that piece? It's the epsilon, exactly. And what we've proven is that for every epsilon, it would work. For every epsilon, if given enough steps, it will be smaller. That's proving it tends to 0, right? Because it's larger than 0 and smaller than epsilon, that's an area of 0. And after enough steps, it will be in the area. But you're right that Euclid did not really say limit. but it did the very same idea. So we'll do something else. Could be looked at as it has some similar ideas, I think, but it doesn't look that way because it's very algebraic. We will use an algebraic argument for this old notion. I think what I like it about the most, why I like to speak about it is to give Euclid his credit. And all the ancient Greeks, they already knew this stuff. So you feel that you learn calculus, but you actually learn Euclid still. Okay, so Bernoulli's close enough. What? Bernoulli's, oh, right, thanks. Inequation. And given a larger, oh, I don't like it. Given R larger than each letter I don't like.
B for Bernoulli.
No, you know what? Yeah. Given B larger than -1, then for all n, it is true that 1 plus b to the power of n is more than 1 plus n times b. Why is it similar? Because it's n copies of b, but it's not the same as what Euclid said. But like I said, there are some connection. Doesn't matter anymore. Okay, so that is called Bernoulli inequation. I say, are we supposed to just take you by your word or Bernoulli by his word? No, we'll prove it, and we'll prove it using induction. That's why I asked you to learn mathematical induction. And why is it important? I will prove afterward, but now I will just tell you, this is some, if b is positive, then this is some number larger than 1, and it's larger than 1 plus infinity times b, which is always infinity. Then using the sandwich theorem, we get that this also tends to infinity, and that will prove this. You can look at 1.00001 as 1 plus 0.0001. And by Bernoulli, it's larger than 1 plus n times, this is 1 over 100,000. Infinity over 100,000, it's still infinity. Okay, so that's the idea. And why 2 over 3 to the n goes to 0, we'll talk about that as well. Euclid started with the 1 over 2 goes to 0, and the modern version starts with the infinity and then deduce about the 0. You will see in the induction step. You don't have to, and I actually don't use it for the -1. But it's the most natural way to say it. It's actually the actual Bernoulli inequation, sorry, is also true for rational numbers. It's more than that, but that's enough for what we need. Okay, and so proof by proof by induction. Okay, induction. So for how do we do induction? Induction. First, you make sure that the first step holds the basis, and then you say, if it ever works, then it must work for the next step as well. That's exactly what we're going to do, and that means that every step makes the next one work as well. So for the first step, the first, it's not step, the first claim, I would say step is the move from one claim to the next. So for the first claim, yeah, I know, but I dislike how, in Hebrew as well, basis, but I dislike how induction becomes so formal and then you don't understand what it says. And many times people ask me, does the base has to be n equals 1? No, it's the first claim. My first claim could be for n equals 16, I don't know. Okay, but it's just language stuff, it doesn't. So for the first claim, n equals 1, indeed, 1 plus b in the power of 1 is larger or equal to 1 plus 1 times b, because they are equal. Agreed? Now, given an n such that 1 plus b to the power of n is actually larger than 1 plus nb. So the claim is that it works always, and now I'm saying, given a certain number for which it works, see, we need to prove that we can take a step. That we can take a step, meaning that 1 plus b to the power of n plus 1 also larger than 1 plus n plus 1 times b. That's the idea of induction. Induction, basically, we say is the first claim holds, and then given a random claim that works, I can take one step forward. That's all I need to do. Because if I can always take one step forward, then it's true for in perpetuity. Why? Because that's the proof of the mathematical induction. Assume that sometimes the claim is false. Take the first time that the claim is false. One time before that, it was true. So I should be able to take one step forward. And so that's the idea. In any case, now I'm left with data and what I need to prove. I know for some random n that someone gave me, I don't know what, Yehi, this statement is true for this specific n, and I need to prove this statement, okay? So I'll write it. So we know that 1 plus b to the n is larger than 1 plus nb. And here again, students say, but isn't that what you need to prove? No, we needed to prove that it always works. Now I'm given one n for which I know that, okay? That for the given number n, it is true that this is something I know. We need to prove 1 plus b to the power of n plus 1 larger or equals to 1 plus nb. Okay. Now, since b is larger minus 1, then 1 plus b is larger than 0. And we can multiply by it. That's the reason for the more than minus 1. So I multiply both sides of the equation. I know that holds. So 1 plus b to the power of n times 1 plus b larger or equal 1 plus nb times 1 plus b. Do you agree so far? On the left-hand side, obviously, we get 1 plus b to the power of n plus 1. And on the right-hand side, let's open the parentheses, distribution law. 1 plus b plus nb plus nb squared. Agreed? Yes, y obviously, but you're correct, but why obviously? Because this is non-negative, let's just say, right? This is larger or equal to 0. So therefore, this is larger or equal to 1 plus b plus nb. But what is 1 plus b plus nb? Yes. So 1 plus b to the power of n plus 1 is larger or equal to 1 plus n plus 1. Agreed? And we see here why this language is it's actually more easy to understand and follow than the geometric way Euclid did it. And it doesn't mean that Euclid was wrong, but it means it shows why it's so important. There are different types of math. Sometimes algebra is better, sometimes geometry is better. I think here, obviously, the algebraic expression is easier to follow. It's not that it's impossible to formalize this using induction as well, but it would be more cumbersome, I think. Okay. So therefore, conclusion, and assume that A is a number larger than 1, then a to the power of n goes to infinity. Why is that a conclusion? I will prove the conclusion. If a is larger than 1, then write a as 1 plus b, where b is bigger than 0. A to the n is 1 plus b to the n. By Bernoulli, it's 1 plus n times b. This goes to infinity, obviously. The b is positive. It's quite important because what would have happened if b was negative?
So they have tended to 0.
No. Just this. No, just this. Infinity times a negative number. What was the limit then? Negative infinity, and then it doesn't tell me anything. To be bigger than something that goes to negative infinity, there is no theorem there, right? But that goes to infinity. I actually did not prove, I usually don't, that n time positive number goes to infinity. That's a really easy exercise. As easy as some when you understand the, the definition of a limit, right? But by sandwich, 1 plus b power of n also goes to infinity because it's larger than something that goes to infinity. Agreed? Now, could the same idea work for a between 0 and 1 to show that a to the n goes to 0? So maybe, but no. And I'll show you why. In this case, if we write 1 a equals 1 plus b, but now b is larger than -1 and smaller than 0, right? Because if a is between 0 and 1, then a is 1 plus a negative number, but not too negative because a is still positive. Therefore, a to the n equals 1 plus b to the n. Bernoulli still holds. because b is larger than -1. So we can say it's larger than 1 plus nb. But what does 1 plus nb tends to this time?
Go to infinity.
Minus infinity. And that is not helpful at all.
I mean, it's not helpful, but still it tends to 0, right?
Yeah, but how do we prove it? Yes, we talked for a while, we didn't prove anything, but it's still true, that's true. Okay. And it's a philosophical question whether something is true before you understand its proof. And as a forest, there are 3-point forest if no one hears it.
If you change all the leaves, is it the same tree?
Yes, yes. Okay. So, and what do we do? That's rather ingenious. I like it as well as, and again, this is an algebraic geniosity and brilliance. Sorry. So, rather than that, assume a, like we said, is between 0 and 1. Therefore, 1 over a, what can you say about that?
Is bigger than 1.
It's bigger than 1. Therefore, what is 1 over a to the power of n?
0.
No, it's infinity because it's larger than 1, right? Therefore, a to the power of n, which actually equals to 1 over a to the power of n. Read. So that stands to 1 over infinity. Which is by theorem 0. Okay. So that's how we got 0. And with the infinity before, using Bernoulli's equation. Okay. Any questions so far? Okay. Next helpful rule, which I don't prove because it's too much work. It's not too, I'll just show you, not work for me, Thomas, but when I said
For my reference.
it's too much not calculus. I'll just show you how it looks. It has some induction and some algebra, but first of all, you need to prove this, which it's that and that. Okay, and then this you don't need.
Okay.
And then it's here, that's what I'm going to prove, and then you need all of this. So it would probably take me a whole hour and a half just for that, and I think it's too much work. So what I will do, I'll give you the rule in a few seconds, and I will explain the basic notion behind it. And the actual proof will be left for the reader. Oh, we didn't finish it, by the way. Until here, that's the end of the proof. Okay, just wanted to make you see. Sometimes I skip things because I don't think you learn something new for them because they are so similar. But this I skip because I think it's too large of a detour than the actual course. So why am I making such a fuss? Because some lecturers say I don't state any theorem which I haven't proved. So they don't show the theorem, right? Because the proof is too much. But I think then the students don't get to see it. I mean, it's not worth it. So I don't have a problem with stating it without proof. Given that I know that you can understand the proof. That's too long. Okay. So the quotient quotient
You,
Ah.
yeah,
Q. And the quotient theorem, not sure if it's called that, not sure even if in Israel Kvala it's well known, so it doesn't matter. The quotient theorem, given a sequence AN, and given the limit of the quotient AN plus okay, the quotient between two adjacent elements, and given that the limit is L, then one, if L is larger than one, then the sequence, the absolute value of the sequence tends to, can you guess?
0.
If L is larger than one, think about two. That means that every element of the sequence is about 2 times larger than the former, right? It tends to infinity. And that's, you see, even this short explanation is a way to understand the proof or the ideas behind the proof. If L is lower than 1, then AN tends to 0. But by the way, to prove both of these, I'll probably even do it during this course when we get to series. The real headache behind the thing is the following thing. And also, if I look at this nth, not square root, if I look at the n root of AN, can you guess what this tends to? Before I write the answer, I will give you the explanation. If AN over AN is about, that's obviously not a proof, but the idea, is about L, then what is AN close to? What kind of sequence, in what kind of sequence the quotient between two adjacent elements is fixed?
The square of L, would it be?
Additions,
The what?
additions,
Reddition?
addition.
What's addition sequence? I don't think so. It's in Hebrew, it's Sidra Handasit. It's a geometric, no, it's saying it's a geometric sequence. Not, I think addition is the algebraic
yeah, yeah.
one. That's the plus. So that's the geometric sequence. That means that AN is about L to the power of F. Because each time then we go to the next step, we multiply by L. It will be exactly that if that equals L and the first element is 1, right? So that's why it's not a proof. It's a general idea. But then what would be the n root of AN?
L.
L itself. That's the main thing behind the rule, but it's quite useful. It's a useful rule, and we will see it a few times. The first two are not that hard to prove, but this one is the one that takes most of the time that I talk to you about. But in any case, you can use this theorem, even though I didn't prove it. And I'll show you now how we can use this proof. Not use this theorem. Example. I'll start with a silly one, and I'll tell you why it's silly and why did I start with it. Say your sequence is 2 to the power of n. Then what is the quotient So it's 2 to the power of n plus 1 over 2 to the power of n, which equals 2, which is larger than 1. Therefore, an tends to infinity. So why is it silly? It seems that the whole proof I did using Bernoulli is not needed. This is much simpler. Why is it a false argument?
Because they use this to make
Yeah,
Bernoulli.
we use the Bernoulli part to prove the theorem. But we need that to prove the theorem. Actually. Why? So why did I show you this? Because it doesn't matter in the test if you remember the order of the proofs. That's a law. You can use it. If for some reason you forgot that 2 to the power of n goes to infinity, there is no problem with using this rule. This specific case probably won't happen, but sometimes such circular proofs are used in the test because you don't remember why is it true, so you use the simplest rule to work with, and that's fine. Okay, now let's do it with something much more interesting, in my opinion, of course. And you, as computer science majors, should know the importance of what is the limit of n over 2 to the n.
It's 0.
It's 0 because this is polynomial growth, and this is exponential growth, right? But how do we prove that it's 0? Can anyone have any suggestion? How do we, yes?
Well, we know that 2 to the 10,
Both the numerator and the denominator tends to infinity. So it's infinity over infinity.
Something logarithm base 2.
I don't see. So you'll probably switch the question to n versus the logarithm of it, which is indeed equivalent, but still just as hard. Not hard, but
Or
so that's other ideas. I will help you. This is an example for the quotient theorem. How about using the quotient theorem? Right?
nah. I mean, nah.
Because it's so elegant. And by the way, just for you to know, later on when we learn about L'Hopital rule, I think that's the most easy way to prove that one. And the quotient rule is good for things that L'Hopital is not good for, like when you have a factorial. I will give you an example in a few. But for now, that's the only way we can do it.
Can we use just one example and say, I don't know, when n is 2,
You just see 2n is bigger than n.
So
So
so you said that always when something is smaller than that, it goes to 0. For instance, n minus 1 over n. You claim that this goes to 0. Numerator is smaller than the denominator.
Oh.
But here it works. It's not what I'm trying to say, it's not a theorem. You cannot say because the numerator is smaller. I have a better example, to be honest. N over 2 over n. That's just half, right? So half is 0. Everything smaller than 1 is 0 from this point forward. Makes life much simpler. No, so okay. No, it's not trivial at all. It's not trivial at all. We all know it because I know.
No, that's not what I wanted to say. I wanted to basically
Yes, continue.
if we take the sequence n,
We take the sequence to n.
Yes.
The-
And divide them.
No, 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 no. Shut up. N plus one is smaller than two to the power of n plus one,
Okay,
and that's basically induction. So
but you're still saying the numerator is smaller than the denominator. But you just went one step forward. Well, you basically told me, forget about the first element. And now the same argument. Not easy at all. Not easy at all. You either need the quotient rule or L'Hopital. But nice try. Let's.
L'Hopital's rule uses differentiation, right?
Yes, yes, it will be in it. I would feel remiss if I didn't say it now because that proves it generally for any number, it's better in some way. But for now, that's what we have, and it's still nice to prove such big results using simple tools, and that's a big result, I think. It's intuitive for us because we know it, I think. I wonder if someone who never learned about exponential growth will think it's so clear. In any case, let's use the quotient rule, law, theorem, whatever. And in order to use it, and for that, we calculate the limit of the quotient. The reason I emphasize the limit is because sometimes students just look at the quotient and they say the quotient is smaller than 1. And that's similar to what you say in a way. And that just only says that the next element is smaller than the former one. That means that the series is decreasing. Does not mean necessarily that it's decreasing to 0. We have to calculate the limit of the quotient, and then we can use the rule. So what is the limit of the quotient? So the quotient is an plus 1 over n, which is, instead of dividing, I will multiply by the inverse. So it's n plus 1 over 2 to the power of n plus 1 times 2 to the power of n over n. Agreed so far? That equals n plus 1 over n times half. And what is the limit of n plus 1 over n? Let's calculate even this. That's the limit of 1 plus 1 over n times half. And now we can safely say the limit is half. Why? Arithmetics of limits. This is 1, this is 0, this is half. So the limit is half, which is smaller, indeed smaller than 1. And therefore, all right, okay. An, which equals n over 2 to the n, goes to 0. Agree?
that one. I was trying to.
I debated with myself if by then you said that's exactly what I meant.
Wait,
I just skipped a few steps.
That's what I meant.
same difference.
N is smaller than 2 to the n. That's what I said, literally. Okay.
I used those words. I don't get it. So we grab the original, which is n over 2 to the n.
Yeah.
And
And
then
then we take the quotient between an element and its former element in the sequence. and we calculate the limit. We
Uh,
basically said that the quotient between two elements is more or less half. That means it's like the geometric series and it tends to zero. That's the idea behind the quotient rule.
so it tends to, 1 plus 1 over n basically tends to 1 because 1 over n tends to 0, and then we multiply it by 1/2 and we get that.
Yeah,
Okay.
that's arithmetic of limits. That we can do safely. Okay. Let's take another example. What is let's say square root of n to the n over n factorial.
Fun.
And I'll remind you, remember, it's not November. And n factorial is 1 times 2 times n. And it doesn't matter now, but I will tell you, and also 0 factorial is 1. Maybe you learned this in discrete math. You learn combinatorics in discrete math.
Yeah, but.
Yeah, we,
So 0 factorial is 1. Because the number of ways to order
0 element is 1.
0 people, yeah. And it's the number of functions from the empty sets to the empty set. It doesn't really matter here at all, but I don't like when when people think the definition of factorial is this, it makes no sense for 0, right? So if I show you factorial this way, then I have to say the actual definition of factorial is the number of invertible functions from a set to itself in size n, and the fact that this is the formula is a theorem you can prove, but all of that does not matter now. Let's change the question. No, it was stupid of me. Sorry. 2 to the power of n squared. I tell you why I changed the question. The one that was written needed the Euler constant, the number e, which we didn't cover yet. Okay, so I changed the question to this. But again, I'm sorry that he left because he must tell me that the answer
what
is
he was doing, right?
obvious. It's either it's either 0 or infinity, but he's sure it's okay. So it's not clear at all, right? The numerator is larger than exponent because it's 2 to the power of n squared rather than 2 to the power of n. And then denominator is n factorial. We're not sure, but the quotient rule will help us. Hopefully.
Oh, wait, no.
So let's calculate the limit of the quotient an plus 1 over an, which is, hold on to your hats, 2 to the power of n plus 1. Not to go, don't give me chocolate. Okay. N plus 1 factorial times the inverse n. He let you hold his hat. She doesn't know what to do with it.
Factorial.
Yes. N factorial over 2 to the power of n squared. Agreed so far?
Mhm.
Now, the factorial factors, right?
N
I'll do it
plus
in
one.
steps. N plus one times. And here we have 2 to the power of n squared plus 2n plus 1 over 2 to the power of n squared, which equals so what is n factorial over n plus 1 factorial?
N plus one.
This is the multiplication from 1 to n. This is the multiplication from 1 to n, and then n plus 1. I will do it again in steps because sometimes students feel this is a formula and they don't remember the formula. And my suggestion, my advice always, if you see factorial, don't be scared, just write the multiplication. So n factorial is 1 times 2 times n, and n plus 1 factorial is 1 times 2 times n plus 1. And now I think it's clear. And next we have 2 to the power of 2n plus 1. Okay, so altogether we have 2 to the power of 2n plus 1 over n plus 1. What do you think the limit of this is?
Infinity.
Why?
Because and we prove that 2 to the n over n is
That's the basic thing. This we can prove. Okay, let's using the quotient rule on this, and sometimes students fear, say, can we use the quotient rule twice? Yes, because this is a series, a sequence by its own. We can use the quotient rule on it. That would be quite easy. One can prove that it tends to infinity. And we're waiting for you to say why this is also clear and obvious. However, you can't just wait for the end and say that's exactly what I thought when I was in the bathroom. No, I'm kidding, but here we have
This is what I wrote in my notebook before I left.
yeah. But what I'm saying is it's again it's the same is going as well. But wait, so let me end my skit. No, seriously, this is again we different
variations.
סדרי גודל, different types of infinity, let's just say. And even if we think that the normal ones are obvious, when we have stuff like that, we have no intuition whether who would be bigger, because this is larger than exponent, but the factor is rather large. And again, we do the quotient. Don't let me interrupt. Okay, so so that it tends to infinity, and so what we've proven is that the quotient tends to infinity, which is undoubtedly bigger than 1. Therefore, n tends to infinity. Just a short note, we didn't use the absolute value since this is a positive sequence. I'll remind you that in the quotient rule, quotient theorem, I use the absolute value in the statement of the theorem. When it's a positive sequence, It's obvious and we don't need to do it. I actually had needed to say that in the last example, but I forgot, so I said it now. Any questions so far? Let's do a couple of more examples. Example. What is the square root, the n root, I'm sorry, of 2? Not what is it, what does it tends to?
0?
Yeah.
No.
1?
Because, yeah.
No,
No,
because
it's not the limit.
because
First
if
of all,
it's-
it's larger than 1.
yeah,
Any n root of 2 is larger than 1.
Yeah.
So it couldn't be. But I have two way to answer it. I will give you the short one. And I will explain to you why you need the quotient rule, but in the test don't have. This- always my advice when you have a root, make it into a power. That's 2 to the power of 1 over n. He's just enjoying himself. Why are you bothering him? Okay. So it's 2 to the power of 1 over n. Do you agree about that?
mm,
What does the power here tends to?
0.
0, right? What is 2 to the power of 0? 1.
Oh,
So it's much simpler, but however, so that's valid in the test. But this is arithmetics of powers, right? I think I mentioned it. If not, I will show you here anyway. Not sure now if I mentioned it or not. That we did. For the example we're doing now. Yes. So I think I said it, but whatever. We will later know that if where is the simplest form here? Just a second, sorry. N goes to A. Ah, it's this one. Yeah, okay. If n goes to A and Bn goes to L, then an to the power of Bn goes to A to the power of L. That's arithmetics of limit using powers. We are not proving that. These are the basic ideas of how to prove that. But like before, while proving it, we're using the quotient rule. So saying that 2 to the power of 1 over n is clearly 1 this way is again a circular argument, but you shouldn't care about this. You can use it freely. Okay, so this is a valid answer to this question. Question? Something which is a bit more interesting, I think. Example. What is the limit of the n root of n itself? Here we cannot go the same way, because if we say that the n root of n is n to the power of 1 over n, which is true, we get here infinity in the power of 0, which is a problematic case because it depends on how large is the infinity and how small is the 0. So that's a problem that does not have arithmetics. You cannot do arithmetics in these kind of cases.
smaller than 0.
Yeah, because it's not really, but it's not really 0, right? It's something that tends to 0. It's not really infinity. It's something that tends to infinity. Okay. What you said sound like a Dr. Seuss. How small is the 0? The 0 is small. Okay, no, I didn't think it's true. Okay, so the square root of n, this n root of n is less clear. And here we will use the quotient law, but we will use the third claim in the quotient rule, this one, which tells us something about the n root of the sequence, meaning that's true, but meaning that we need to use the sequence underneath the roots. We will use the quotient rule on the sequence beneath the roots, meaning that our actual sequence that we use the quotient rule on is n. I think that's the main thing that confuse students the most. They usually try to do the quotient rule on the sequence we asked about, but no, we need to use the quotient rule on n because it will tell us about the square, the n root of n. Look again. If I know that the quotient of the series an tends to L, then the n root of an tends to L. So we need to look at this sequence. And again, I don't need absolute value because it's positive. So the quotient, right. And let's calculate, let's calculate the quotient, the limit of the quotient an plus 1 over n equals simply n plus 1 over n, which is 1 plus 1 over n, and which goes to 1. And therefore, if the quotient goes to 1, this n root of an also goes to 1. That's the quotient rule, the third claim in the quotient rule, which equals, in this case, because we chose an wisely, that means that the limit is 1. The nth root of n goes to 1. Yes,
When you say an equals n, what does that mean?
I look at this sequence. It's not, I'm not claiming that the original sequence equals n. I didn't name this sequence at all. But I'm telling you, I wish to use the quotient law, the quotient rule on this sequence, and we are allowed to use the theorem, any theorem, on any sequence that holds the necessary conditions to the theorem. Here there are none. The theorem says any question, any sequence, sorry, that it's the limit of its quotient is L, then the limit of its root will be L as well. And I just use this law, this rule on the sequence N. I'm allowed. Let me give
But
another.
you're only proving it for.
No, I'm not only
You're only
proving it
working-
for N. I'm using N to prove the theorem I wish to prove, right? Because I can substitute into the theorem whatever I want and get a true statement. Do you agree?
Yeah. But
Okay.
then how does it work with the question?
So how did I identify that that's what I needed to do? The question was about the n root of n. So look at the third part, you see? The question was in this form. And I knew that what was within under the root, that's what needed to be the sequence I used the rule on, right? Because the conclusion is about the n roots of that. Let me give you another example. and it's basically the same thing, but I will word it differently. Let's use the quotient rule on the sequence and factorial. Sami, stay with me. Do you agree, Sammy? Do you agree that we are allowed to use the quotient rule on n factorial? I'll
Yes.
right? It's just any sequence. The rule says it's I'm always true. I'm true for every sequence in the world. So this statement must hold for n factorial, right? What is the quotient of n factorial? Now, and now we don't have any question. It's just an example. Example. What is the quotient of n factorial? It's n plus 1 factorial over n factorial. Do you agree? That equals n plus 1. Where does it tend to? Infinity. Agreed? What does the quotient rule says? First, since the quotient has a limit larger than 1, we can say that n squared and n factorial, sorry, tends to infinity. Do you agree? That's the first law, the first conclusion in the quotient rule. Here it's not really impressive at all. Obviously, n factorial is larger than n. Obviously, it says. But also one might say, one is allowed to say that this n root of this sequence, where does it tend to?
It's
Why? But why? What did the rule say? The rule said if the quotients tend to L, the root also tends to L. That's what the law said. But
It's the law.
yeah, it's not the law. Yeah. The rule, right? Okay. It's one of the things it says, but the quotient rule says if the quotient is L, the n root also goes to L. Agreed? So we found out something interesting here. Oops, I wrote L instead of infinity. And so we found out something interesting, by the way, that the n root of the n factorial goes itself to infinity. So now, Sammy, for the final thing, imagine that this was the question from the start, and then you would say, how can I solve this limit? I will take the sequence underneath the root and do the quotient rule on it. That's the main thing here. Any questions so far? Okay. Now I will go into some introduction. There's so many ways to go at it. I'll go with the one that is closest to where we are. So instead of an introduction, it will be for now another example, but I warn you, we will not be able to solve this example, okay? What do you expect the n root of n factorial to be? The n root, or that I will just say and not write. when you take the square root of the multiplication of two numbers, it's some kind of average between them. If you take the third root between the multiplication of three elements, it's again some kind of average. It's actually the geometric mean. So the n root of n factorial, which is the multiplication of the first n numbers, it's some kind of average. And it makes sense that it goes to infinity because you add numbers. But at what speed does it go to infinity? What would be the limit of the n root, sorry, of n factorial over n? Okay, I'm saying what is the connection between the average and the number I'm at, right? The average of the numbers up to till me and me. Could there be any connection between the two? Do you have any guess?
We the difference should be the nth root of n.
What is the limit of this? I'm asking what is the limit of this thing. And I gave you a connection between the two. I said this is the average of all the numbers until n. It's obviously smaller than n, right? Because all of the numbers are smaller. But the question is how much smaller? How much smaller than n it will be? What would be the limit of these two things? The average until n versus n.
0.
So that's an interesting question, right? So how can we use the quotient rule? What's the problem here? What I told Sammy before, if we have the n root of something, we can use the quotient rule on the sequence beneath the root. But here we don't have it exactly because we have a root and we have a fraction. So the first thing is kind of, wouldn't it be nice? We would like to have one big n root in order to use the quotient rule, right? What would be underneath the n root?
N factorial
And
and n squared. No, n to the n
n to
power.
the n, exactly. Okay. That is basically the average of 1 over n, 2 over n, 3 over n until n over n. The geometric average. Okay, so now let's use the quotient rule on the sequence beneath the root. Okay, so let's call it Bn because now an is taken. So Bn is the sequence beneath the root, and without calculation, the rule says that if the quotient Bn plus 1 over Bn tends to L, then the root is on fire. Then the root of Bn also tends to the same L. That's what the quotient law promises us. So if I choose this to be the sequence, if I will be able to find the limits of its quotient, then the limit of the root, which is actually the sequence I was asked about, will also go to the same L. So let's figure out what is the limit of the quotient, and we will not be able to, but it's an introduction, like I said. Okay, so what is Bn plus 1 over Bn? So Bn is that thing, and Bn plus 1 is n plus 1 factorial over n plus 1 in the power of n plus 1 times the inverse n to the power of n over n factorial. Agreed? Let's do some algebra. We have n plus 1 factorial over n factorial times n to the power of n over n plus 1 in the power of n plus 1. What is n factorial, n plus 1 factorial? Then you should say that's exactly right. Okay, sorry. What is n plus 1 factorial
N plus
over
one.
n factorial? That's n plus 1.
I don't say it because
Yeah. I, you mean I don't care to dignify you with an answer? Yes. Okay. What can we do next? This is a bit confusing algebra wise.
We can take n
Yeah.
plus 1 out and do n plus do it over n plus 1 to the n, yeah, and here it's a bit messed up.
Now we have n over n plus 1 to the power of n. Agreed? Now let's look at the limits. The limits within the parentheses is, what does this tend to? 1. And the power, the base of the power tends to 1. And
Infinity.
infinity. This is another problem because it matters how fast this is going to 1 versus how fast this goes to infinity. Okay? And we don't have the tools yet to figure that one out. Okay? I just wish to tell you at this point and to notice that 1 over n plus 1 to the power of n is n plus 1 over n to the power of n, which is 1 plus 1 over n to the power of n, which you still don't know, I think. Maybe some of you will know this. But like I said, it was the introduction to this very important limit. This is actually a very important limit that we will study.
I mean, I'm sure you're right, but also can't we just say that n plus 1 to the n is at least n to the n?
What do you think the answer is, first of all? And then I will tell you no, and it will... No, seriously.
No,
What
but
do you think? What do you claim this is?
I mean, we didn't see Pascal's triangle yet, but like we know that n plus 1 to the n is like blah blah blah,
Yeah.
a combinatorics about, but the first
Blah 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 combinatorics.
the
Blah
first
blah blah.
the first term is n to the n, and all the rest doesn't
I
matter.
like this guy.
Yeah, right? That's fine, yeah. So blah 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 combinatorics, yes, and blah 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 combinatorics, but what is the answer?
It tends
Ooga booga.
oh yeah, it tends to 0.
No,
It doesn't?
Thomas
no.
hates to get it wrong.
Yes. Thanks. So I won't leave you hanging. The answer is 1 over e. Okay. So it's not blah 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 combinatorics. Sadly.
God damn it.
Yes. Okay. See you. Thursday we meet.
No.
When are the classes?
Uh,
When Sunday. So we did. So see you next week. Okay.
Will we have no, great. No, a class because we didn't have one on Sunday.
Oh no. If by the end of the semester I'll see that I'm not finishing the material, then maybe. But usually I don't switch a class for a class.
Well, that's a simple right. Add a clear response. Can you tell that to Marie?
Yeah, because she just needs to do
This is me
that much
every day.
Yeah.
Everything is fine.